about hydrogen as a spectroscopic entity, right? Something that we do spectroscopy. And that's a really important way to interpret hydrogen because that's historically how we understand hydrogen is two lights. We'll see that. I'll kind of give you guys a historical perspective on how the theory of hydrogen is built purely from spectroscopic results. So we'll talk about the spectroscopy of hydrogen, and that will allow us to dig a little deeper into hydrogen and derive and start thinking about spin. Notice we've not talked about, I've introduced spin to you guys. We haven't included spin in the hydrogen atom. So spin doesn't really appear until we start talking about energies. And there it becomes extremely important. We'll learn about a certain trend that appears in an atom's atomic energy levels where the spin affects the energy levels of hydrogen. Certain type of special coupling or spin orbital coupling. We'll talk about that next class. And then that'll be a really, really good way for us to leverage that our conversation about hydrogen, talk about other atoms, heavier atoms, multiple electrons. Because again, we'll want to use spectroscopy, energy levels to understand how can we take helium and apply it, how can we take hydrogen and apply it to helium or lithium or some of the bigger atoms, right? How can hydrogen be our framework for atoms? I think a really good way to do that is through energy levels. But let's recap very briefly where we were about a hydrogen atom. We've spent a long time making momentum. Last few lectures we've been tackling the radial problem. Just remind you what that is. We're basically not thinking about things in terms of angles anymore. We're thinking about the energies and the potentials of the electron as a function of radial distance from the proton. And there's two forces that are combined. There's an attractive potential between the proton and the electrostatic potential, which goes as -1/r. It's a negative potential energy, which means it's attractive, and it gets bigger as the electron gets closer to the proton, as they get more and more attracted to each other. But there's an equivalent force because of the angular motion at some fixed amount of angular momentum. You have this centrifugal force that's pulling the electron away from the center. And that centrifugal potential goes as 1/r². So at close distances, the centrifugal potential dominates, right? And this is why the electron doesn't get sucked in to the proton. It's because of its centrifugal force getting polynomially larger, r² larger, every time it gets closer and closer to the proton. So as it gets closer, the centrifugal motion is pulling it out harder. Right, so that's why it doesn't get sucked in, because the centrifugal potential is more repulsive at close distance than the electrostatic potential is attractive. Okay, so we're always looking for balances between these two forces, right? A stable orbit is where these two are compensated equally, where the centrifugal force is compensated from the electrostatic. We went through a long kind of conversation about how we would calculate this radial function, right? We're thinking about these wave functions that are functions of r. What do the probabilities of the electron look like as we move away from the proton? We go through a bunch of math. And what we come up with after we do all this math is this rather complicated equation for the radial part of the wave function. But we can just break it down into small parts. I think it's more easy to think of it that way. It's a long function that's got some polynomial dependence in R, and it's also got an exponential. But again, we can interpret each of these pieces separately. Here on the left in purple, we have the normalization constant, right? This is just a number. So that when we square this and integrate it, we get 1 back. Right? Remember, the probability has to be equal to 1 over all space. So that just normalizes the function. We have this close distance relationship. We saw that when the limiting case where the electron is very close to the proton, the wave function should look like r to the L. Right? So it should look like a polynomial in R. And then at the long distance, it's truncated as both of the potentials roll to 0. Right? At infinite distance, there's no interaction at all. And so your probability will go as e to the -r exponentially k. Okay, so at close distance, it looks like a polynomial. At long distance, it looks like a decaying exponential function. And then we have this connective tissue that brings in the two limits together. right? We need an additional function that it specifies the intermediate region of the wave function between those two limits. And it needs to be set up so that the whole function across the entire domain, 0 to infinity, is smooth, continuous, differentiable, right? The normal function you can take derivatives of. And a derivative exists everywhere. So we include this additional, when the math works out, you include this additional polynomial called, which I call a Laguerre polynomial, all right, which is just like that special polynomial in the harmonic oscillator wave function. It's this thing that orthogonalizes the functions so that the 1s orbital is completely different from the 2s, which are different from the p's, right? They're completely separate orbits, if you will. This function provides that orthogonality and also provides the oscillatory wave-like behavior we would expect for a wave function. We would expect the wave function, right, to have some sort of wave. And it should oscillate in the region that it exists in. And this Laguerre polynomial adds that oscillatory function to it. So what we have in general, it's not too complicated. We have, well, I mean, it looks nasty, but basically it's a big number. There's a polynomial that's a function of r to the L or r to the n in this case over here. So you have this polynomial that's a function of r times an exponentially decaying function. So it's just a bunch of parameters, a bunch of r terms and an exponential at the end. We looked at some examples of these at the end of class, where I've defined this unitless distance rho, which is r over this a naught number. I'll remind you what that a naught number is because I did it in the class. And so for the 1s orbital n equals 1, it just looks like an exponentially decaying function. The polynomial on the outside is just 1. Right? The order of that polynomial is 0 for n equals 1. So you can just think there's an implicit 1 in here, or r to the 0. Right? This is just a decaying function, right? And it's spherically symmetric. There's no dependence on any of the angles. So it just looks like a decaying sphere. When we go to n equals 2, we include now a polynomial that's linear in R. Right? So in some sense, the polynomial is to the power n minus 1. So we would expect for the 3s orbital that there would be a quadratic function here, which is true. And what this does is it provides now some oscillatory behavior to the wave function. Now this function has, right, the only place where the 1s orbital wave function is 0 is at infinity. Here, this wave function is 0 at infinity, but it's also 0 at where rho is equal to 2, where r is equal to 2a naught if z is 1. That's what that would mean. And so this function goes to 0 and changes signs in the middle, this wave function, which implies like a sine wave, right? A sine wave also changes signs and oscillates. And so we're seeing some of that oscillatory behavior start to appear. It isn't fully oscillating yet. It's only doing, in some sense, one period of the wave, half a period of the wave, but it is a whole period of the wave. Sorry, no, 3/4 of a period of a wave. Yeah, 3/4 of a period of a wave, but it is in fact oscillating. And we see that in the 3s, we see that as well. The 3s orbital has a quadratic function here, p squared, rho squared. It means it's going to have 2 zeros instead of 1. It's going to be 2 points r or rho that are finite and non-zero, where this function goes to 0 for the 3s orbital, and you get 2 nodes instead, right? You get a place where this goes negative, and then it goes positive, and then decays. Right? You're starting to add little half periods of your wave every time you go up and in. Right? But when we take the interesting thing, we'll have to go back and look at this again. Since we look at the 2s orbital, we have 1 node in the middle. Right? So there's a place where the electron doesn't exist. If we go to the p orbital, the equivalent p orbital for n equals 2, there is no node. Because this is rho, this is r e to the minus r. This is only 0 at r equals 0 and r equals infinity. So in the p orbital, that node that appears in the middle of the s orbital appears at the beginning. Right? So in the p orbital, there's no possibility to find the electron in the center based on this wave function. which is exactly the thing that we typically draw, right? We draw this lobe-like structure for the wave function where there's a node in the center. So again, there's no possibility the electron is there in the middle, right? But we lose, in some sense, we lose that oscillating structure here, right? It's not oscillating at finite r like this 2 is. It equals the 2s orbital does. So there's a trend, right? There's some trend with the way how the function oscillates depending on the value of n and l. Right? We'll look at that more carefully today. Now, you may wonder why this matters. Why do I care about these nodes? Well, it turns out when we get to molecules, thinking about how the orbitals look like where electrons exist tells us a lot about the bonding that these orbitals can participate in. I want to try to emphasize that to you today as well. That the fact that these higher order s orbitals, for instance, have these oscillations, right? These nodes actually affects the bonding characteristics of atoms whose electrons are in these orbitals. Right? We'll look at that kind of carefully today. We'll obviously explore it more in detail later this semester or this month. All right, so what I want to do today is I want to think about probabilities, right? I want to think about where an electron is in a given orbit. And we've drawn these pictures already, right? I want to just do a little bit of math with it and play around with these wave functions a bit to understand how the electron exists. Where does it exist typically in a given orbital? So let's go ahead and look at the 1s orbital, which is the easiest one, of course. Right, so let's consider something. Let's think about probabilities, right? We're going to have a box. We'll call this psi 1s. Right? We have a box, and we're going to take an electron, a hydrogen atom in its 1s orbital, right? Its ground state, a whole hydrogen atom, and we're going to image the electron. We're going to take little snapshots and measure where the electron is. We're going to image the orbital. Right, and when we take an image, right, that's what we're doing is we're measuring the distribution of positions, right? So the probability let's think about this, right? So the probability of electron at XYZ, right, by our definitions from back in the day, is equal to psi 1s squared times dx dy dz. Right? And the idea is very simple. If we want to ask the question, here we have an electron here, and when we want to ask what its probability is, right, we just have to measure the value of psi squared at x, y, and z, and then build a little cube around it. Do I have a cube box? No, I don't. We build a little cube around it of size dx, dy, dz, and the total probability is equal to, again, the value of psi 1s evaluated at this point squared times this volume dx, dy, dz. We have this little volume element. All right, we'll call that dv. Little volume, right? And the reason why we have to append this little volume to it, right? The reason for this is the fact that the probability the electron is anywhere is the integral over the entire box dx, dy, dz times psi 1s squared, right? From 0 to infinity. Or sorry, minus infinity to positive infinity. right? So we need to have that little differential, that little box, so that when we integrate probability across the entire space of the problem, that we get one out, right? This needs to be equal to one. All right, so there's always this implied tiny infinitesimal volume element that you multiply your probability by, your psi squared by, right? But we typically neglect this when we do calculations because it's just a linear function, right? It's just x times y times z, and this is really, really small, so we can just disregard it, right? The volume is just a little cube, right? So we can change the size of that cube by integrating it, right? But if we're just going to calculate the probability at one tiny infinitesimal point, then we can just kind of think of dV as being one, it's a volume of one, tiny little point size volume, and we can just evaluate psi squared for it straight up. Okay, so we don't ever have to think really about x, y, and z. We can just plot psi squared, and the point of psi squared, the value of psi squared at every point is its probability. Right, but here's the problem. In the hydrogen atom, we're not in x, y, and z. Right? We're in spherical coordinates, r, theta, and phi. So the problem with this analysis this is r, theta, and phi, is that dx, dy, dz, the size of this infinitesimally small volume is not equal to dr, d theta, d phi, right? There's a unit conversion, right? X doesn't correlate to r, y doesn't correlate to theta, z doesn't correlate to phi. There's a conversion between all of them, right? All three of these parameters, in some sense, depend on the values of x, y, and z together. So this conversion, this change of variables, isn't just one-to-one. You have to do the chain rule, right? When you when you take a derivative of r, you got to take a derivative of r with respect to y, and respect to x, and respect to z. So there's an additional factor from the chain rule, and this is what we derived when we started talking about spherical coordinates, but rather this little square volume element around our spot, a little probability volume in spherical coordinates, is actually r squared sine theta, dr, d theta, d phi. So in spherical coordinates, there's this additional factor in this volume of r squared sine theta. So what we would actually say, this would imply now that the probability of finding the electron at r, theta, and phi is equal to the value of the wave function evaluated at r, theta, and phi squared times r squared sine theta, dr, d theta, d phi. Right, so there's this additional factor of r squared sine theta that we always need to multiply the wave function by in order to properly do the unit conversion, if you will, or the coordinate transformation between Cartesian coordinates, rectangular coordinates, x, y, z, and spherical coordinates, dr, d theta, d phi. There's always this additional volume factor here. Right, so this right here is our dv. A little volume element of probability that we integrate. So let's take this math and now think, all right, so what I want to do is now I want to calculate the probability of the electron at some value r, right, independent of theta and phi. Right? This will tell us something about where the electron is along its radial coordinate. Remember that the electron is the theta and phi dependence is separate from r, right? Remember, we separated them. That's how we had this whole problem. So we can always calculate this, right? We can always say, let's just get rid of the theta and phi dependence and just think about the probability for R. Right, so how would we do that? Well, so first, let's just separate the function. Right, we'll write psi1s which is a function of r theta and phi. We'll write it in terms of its spherical harmonic, which is 0, 0, theta phi, times the radial function for the 1s orbital. All right, so if there's two functions now, we'll just split it into two like we always do. Of course, the function for this right here, we can write that down. So for y0, 0, is just square root 1 over square root 4 pi. Or it's just a number. Right? And the radial function is just the difference, which is, let me get it right. So it's 2. Yeah. 2 for hydrogen, it's 2, 1 over a naught to the 3/2 e to the minus r over a naught. A very simple function. All right, so now what we want to do is all we have to do now is just think about our function in terms of r. All right, so we'll take this probability, and this is going to be the integral over the entire system, dr d theta d phi. All right, we first integrate around r, that's 0 to infinity. Theta is 0 to phi. And not phi, pi. And phi is 0 to 2 pi. Right, times our function. 1 over the square root of 4 pi times 2, 1 over a naught to the 3/2 e to the minus r over a naught. Remember, we square this, and then we have an additional factor of r squared sine theta, right, from the volume. So this is our psi squared. We have r squared sine theta, and we're integrating over all the coordinates. But the nice thing about this, of course, is that all the r dependence, all the radial dependence is separate from the theta dependence, right? Just cut it here. Everything on the left is r, everything on the right is theta. So I can rearrange this integral. So this is going to be the integral from 0 to 2 pi of d phi. The integral from theta 0 to pi, excuse me, I'm getting my Greek letters mixed up, of sine theta d theta times the integral from 0 to infinity of, let me do the math here. So that's 1 over 4 pi times 4. So that's 1 over pi, 1 over a naught to the 3rd power, e to the minus 2r over a naught, r squared dr. Okay, so I just separated everything out. Right, separated by variables. Well, these are really easy to calculate. Right, the integral of phi from 0 to 2 pi is just 2 pi, because it's integrated, it gives me theta or phi. 2 pi minus 0 is 2 pi. So we get a 2 pi. Right, the integral of sine is cosine. Cosine of pi is -1, minus the cosine of 0, which is 1. It's -1 minus 1, minus 2. All right, it's 2. Sorry, it's 2. Apologize. 2, so we get a 4. The 4 pi, And then what we have left is this integral over R. dr R squared, 1 over A naught to the third, e to the minus 2R over A naught. Okay, and if you look at this, this looks like 4 pi times the integral of dr R squared times the square of the radial function. All right, so this is our little radial probability density, dr R squared times the radial function. So what we can say, we'll solve this in just a second. All right, what we can say is that the probability of an electron at R is equal to R squared times psi squared times dr. All right, so every time in spherical coordinates, anytime we want to calculate a probability in a radial direction, we just need to multiply it by R squared. Right, so there's an additional factor of R squared that appears. Compare this to the probability of the electron in one dimension X, which is just a rectangular coordinate, right? Just a line. Is psi squared dx. All right. So all we're doing here is taking something that's on a line, it's R, the line R, but it's something that's spherically averaged, right? The R can point in any direction. So we need to consider the preference of R being in a certain direction, which is the spherical harmonic part. But what we're doing is we're integrating over the entire sphere, right? So it doesn't really matter what the spherical harmonic is doing. We're ultimately taking an integral over theta and phi of the angular part of the wave function squared, but the wave function is normalized. So this is just going to integrate to 1. Okay, so we don't have to worry about the spherical harmonic part at all, if you think about the radius. Because when we do this integral, it just goes away. So the only thing that's left therefore is just this radial part. And the only difference between a function in XYZ space and a function in R space is that we multiply by R squared. It's the only difference. So there's an additional factor of R squared that appears. All right, let's go ahead and finish this calculation. Let me just take this integral and let me make one more page. So we have this integral, and I can go ahead and substitute in things. This ends up being 4 over A naught cubed times the integral from 0 to infinity of R to the third times e to the minus 2R over A naught dr. I can do some U substitution here. Great. And you get 4, and this integral ends up being the integral of 4, integral from 0 to infinity of u to the 3 e to the minus 2u du. All right. Well, this is an integral you have to do by parts. Right? You got to get rid of this polynomial part, so it's going to be 1, that'll be u squared, then u. Yeah, so 3 integrals by parts, but Wolfram alpha will do this no problem. Super easy integral for Wolfram alpha to do. You can look it up in the table. Not too bad, but what you find now is that the average value of R for the 1s electron, so it all works out, is 3/2 times this number A naught. All right, the Bohr radius. All right, so what this says is that in the 1s orbital, the electron on an average, again, it's delocalized, it can be anywhere, but on average, it's at this 3/2 this value A0, right, this Bohr radius. Let's go back and remind ourselves, since I kind of threw it at the end, what the Bohr radius is. Right? I like to call this 3/2 A0, or this A0, is what I call the chemical length scale. Right? The idea is that if you have two hydrogens, right, and let's say the distance from here to the electron on average is 3/2 A0, and the electron for this one on average is at 3/2 A0, right? Then if we share the electrons and think that they're like equivalent, then the distance from here to here is 1.5, 1.5. This says that it's around 3 angstroms, right? Which is a little high, but experimentally, right, it says that the bond between two hydrogens should be on the order of about an angstrom. Experimentally, it's about 0.9 angstroms, right? So the idea is that 1 angstrom is like a chemical bond, right? This is why we always see this number pop up, is because in the hydrogen atom, the electron in its ground state typically sits around A0, right? So when you bring two molecules together, two atoms together, their bond is going to be around 2A0, right? Let's go back and look at the value of A0. It was something I threw at the end of class. Again, I'm sorry. Let's spend our time talking about it today. That's at the end of this slide deck. Right, the Bohr radius is a number that's, again, experimentally measurable, A0. It's about 0.53 angstroms. So if you've got two electrons that, let's just say, give or take, sit at about A0, which is actually the most probable location. It's not the mean, but it's the most probable location for A0. You've got two electrons sitting at roughly A0. They're both 0.5 away. When you share, that means that the total bond between the two atoms is going to be about 1.06 angstroms. And that's exactly a rough bond length, right? Those bonds are about an angstrom. Some are maybe 1.8, maybe 2. But typically they're on the order of about 0.8 to 1. Right? And so that's entirely, that scale of bonding is entirely set by this Bohr radius, right? The average attraction between the proton and the electron, compensated by the centrifugal potential, puts the electron on average at A0 in the ground state. And that number is fixed, right? It's determined by a bunch of constants. A0 is determined by how effective you can transmit a current or electrical energy through the vacuum. That's epsilon naught for permittivity. H bar squared, of course, is our fundamental unit of energy in some sense for our electron or for any quantum mechanical system. H bar squared is proportional to L squared, angular momentum, so it's always going to show up in calculation. That means it's quantum. And then it's truncated by how strong the charge is. E is the charge of the electron. Every electron brings to the table a fixed amount of charge, and the proton correspondingly brings to the table the opposite charge, +1, -1. That's how much charge we bring in. And then it's also truncated by the mass of the electron. That tells you kind of about the centrifugal force. The centrifugal force gets smaller the heavier the electron is. So A0 is determined in some sense by the ability for the system to transmit electrical energy, electrical force through the vacuum between the proton and the electron. That's E0, and it's divided, and that's E squared, right? So E squared is the amount of charge that's being delivered between the two. Epsilon naught tells you how efficient it is to transmit that charge between the two particles. H bar squared, again, just tells us we're in quantum mechanics. And m sub e, right, h bar squared over m sub e looks like angular momentum. Right? H bar squared is proportional to angular momentum squared. Angular momentum divided by mass, 2 times the mass, is the energy. So h bar over me in some sense is this centrifugal term. It says something about how the centrifugal force compensates relative to the electrostatic force. But both of these forces come into play here. And the fine balance of all of these constants in the universe puts us right about 0.5 angstroms. Right? So chemistry is set. Planck scale of chemistry is set by this number. And it's completely defined by the physics of the universe. These are all fundamental constants. They are unchanging. So this is why every bond is 1 angstrom, basically. Just makes sense. If somehow the electrostatic potential was stronger, if the electrostatic potential was stronger, maybe you are in a dielectric that isn't a vacuum, something that's more conductive, and where epsilon 0 would be bigger, that would push this electron further out. The electron was heavier. Right? It wouldn't have as much centrifugal force that would pull it in. The length would be smaller. A very, very fine balance between multiple different things that all just come together harmonically in this like magical number that just puts us right in chemistry, right? So it depends on how you look at this, right? You might say, oh, this is really convenient. This puts us exactly where this gives us a prediction of how long a bond is going to be. That's really nice. So it's just convenient that chemistry works out. I like to think of it the other way. Physics set where chemistry is. Chemistry is only dependent on the values of its constants. And so these constants are what determine how chemistry works. Right. So we somehow have, from first principles, derived the length scale of chemistry. And we'll see that time and time again. You can define a length scale for chemistry. You can define a time scale for chemistry as well. And an energy scale. We've already looked at energy scales for chemistry. You can also define a time scale for chemistry as well. And that'll be something we'll look at a later point. Time scales. Okay. So what I want to do is just look at some of these probability distributions for the radial, right? And so this will give us, right? I want to go back to this picture from last class, right? These are these probability density plots, right? These are angular plots. This shows you, this is like a cut through the sphere, like a bird's eye view, cross section, MRI, X-ray of the orbital, theta and phi. It's the X and Y axis here. And R is the distance away from the center. I want to look at these instead. I want to look at them from the perspective of moving along radial direction. Right. So instead of plotting them in an angular plot like this, which I find very convenient, what I want to do is I want to look at the functions through a cross section where I take this picture and I cross through it like this. Right, and I have a line that crosses through it. Right, so I want to take cross sections, one-dimensional cross sections of these two-dimensional plots, right, along the radial direction. All right, that'll give us a little bit of insight about this oscillatory structure we see here. I have a really nice picture for you guys. Last class I drew them, and then I found a much better picture in a book that I'd rather just show you guys from the book. So let me go ahead and pull it up. Here we go. Excellent. So these are really nice. I think these are really nice plots from the textbook that I've given you guys that some of you have and some don't. So these are radial distribution plots. So these are plots of, that's a terrible color for this. Right, so for instance, this is equal to R squared times psi 2, 0, 0, the 2s orbital squared, and they're divided by a naught squared so that they're unitless. Okay. And so here are some radial distribution plots for our most simplest orbitals. So one interesting thing is you can see, right, so these are all on roughly the same scale. So the X scale here is R over A naught. So it's how many units of Bohr radius you are. You can see that for the 1s orbital, there's a peak, a very, very well-defined peak. And that peak is actually a naught here, right? It's a little different than the mean, right? The mean is 3/2 a naught for 1s, right? So the mean is kind of like over here instead. And the reason why the mean is shifted to the right a little bit relative to the maximum is because this is not a symmetric plot. Remember, at short distance, it looks like a polynomial. And on this axis, it looks like r squared. And then on this one, it looks like e to the minus r. Right? So we have a plot that increases more rapidly than it decays. Right? So there's more area under the curve on the long end than there is on the short end. If I cut the function in half by its maximum, there's less area over here than there is here. It's biased towards the long end. That should make sense. Again, the electron doesn't want to get too close because the centrifugal potential is much stronger than the electrostatic potential. So the long distance behavior of the electron is preferred. It prefers to be further out than it is closer. So relative to the center, the mean is slightly shifted to the right. Because it tends to be on the right side. And so you can see now, right? So the 1s is at A naught, right? This is why we say the bond again is roughly an angstrom, because on the most probable place to find the electron in the 1s orbital is right there at the peak. A naught. Then we can see in 2s and 3s, here, right? You're starting to see that oscillatory behavior appear. Right? There's 2 nodes for 2s. There's 1, 2, 3 nodes for 3s. And if we saw 4s, there'd be 4 nodes for that as well. But you can see here, like for instance, for the 2s orbital, right? There's actually 2 peaks. One is at, I don't know what that's at. That's like 6 A naught. It's roughly 6 A naught. And then there's a small peak here at 1 A naught. And so, and you can see as the electron gets to higher and higher orbitals, this is 5, 10, right? The peak here is about 12 A naught. Right? As the electron goes up in orbit, an N number, right? It's going to a higher orbit, higher energy orbit. It's further away from the center. And so the distribution shifts to the right. Electron on average, as it goes 1s, 2s, 3s, 4s, it's moving further and further and further away. Now, one thing that I find very interesting is if you look at the progression here from 2s to 2p, 2s has 1 node. Right? Well, it has 2 nodes because the other one, it can't be at the center, right? So it's got 2 nodes. But 2p only has 1 node. And then let's look at 3s, right? 3s has 1, 2, 3 nodes. 3p has 2 nodes. 3d has 1 node. So the number of nodes in a hydrogen wave function is equal to n minus L minus 2. All right, let's double check that. Let's look for the 1s. 1s only has 1 node. N is 1, 0. Oh, this doesn't work. Hold on a second. Is this plus 2? I know how to fix this. It's -1, excluding r equals 0. Right. So in general, no electron will ever be at the proton. Okay, so let's just exclude that as a node. So this has 0 nodes, this has 1 node, this has 0 nodes. So for the 1s orbital, n is 1, L is 0. So you have 1 minus 0 minus 1, that's 0, 0 nodes. 2s has 1 node, 2 minus 0 minus 1 is 1. 2p has 0 nodes, that's 2 minus 1 minus 1, that's 2, and so on and so forth, right? So what I like to think about is, in some ways, is that the 1s, 2s, sorry, 2p, 3d, 4f, all are spherical-like with no nodes. All right, so there's going to be an orbital in each one of these groups, right? Not all of them. All right, we'll have to think about that a little bit because, again, there's 5 of these and 3 of these. But in general, relative to their angular distribution radially, they look like 1s orbitals. They're kind of smudged out, right? The 1s orbital is very sharp, which is why it's called S. S means sharp. It's actually what it stands for, right? And that's because, again, the radial distribution is very sharp, right? It decays very rapidly. And you can see that as we go from 1s to 2p to 3d, the thing kind of smears out. P means principal, I don't know why. D means diffuse. You can see it's diffuse, right? It's less sharp, it's more spread out. But again, it just kind of looks like you've taken this 1s orbital and you've just stretched it out. Right? The 2p orbital and the 3d orbital just like stretched out 1s orbitals. Right? This has deep consequences for bonding. Deep consequences. Right? I want to talk a little bit about this concept. Let's consider, for instance, two systems that interact through these spherical-like orbitals versus ones that have interactions, rather have orbitals that have nodes in them that oscillate. Right? Let's think about how bonding works in these situations. Again, we're gonna formalize this in a couple weeks. But I think this is a nice taste to think just very qualitatively about bonding. We know that bonding is you take 2 atoms, you bring them together, and they share electrons. What does it mean for them to share electrons? It means that there's some probability in between the 2 atoms that where the probability is growing, some growing in that probability center where the electrons are shared. You're going from a system that has 2 atomic wave functions that are non-interacting. You're bringing them together and allowing them to interact, which will build some probability of the electrons being in the center. Right? So the idea is that we want to have this addition of 2 wave functions together that's constructive in the center, that we build up probability density between the atoms. So let's look at some examples. All right, so let's look at H2. We have 2 atoms, HA and HB. Okay, and they're both in the 1s orbital. Right, just regular hydrogens. Right, what would the wave functions or the R squareds look like? What would the probability densities along the R direction look like here? So let me just draw some axes here. So those are, and we know the wave functions go to 0. Let's make this one blue and this one green. So the blue one looks something like this. And the green one is the same, but just mirrored, something like this. Right? So when we add them together, we take psi 100 and then add it to psi 100. Right? We're going to overlap those 2 orbitals together or share together. Right? And what do we get? Well, we just get some smooth addition between here and here, where they kind of overlap. So we get this function where both of them add together. Maybe it looks something like this. And this would be the wave function, if you will, for the bond. This is the psi H2 bonding. Right? And you have this nice overlap, right? You have this nice overlap between the two functions. You have lots of probability in the center. Right? This is covalent. This is a covalent bond. Right? You have sharing of electrons in bond. Right? Equal sharing. It's a covalent bond. Right? And they just add naturally, right? Because they're both positive and they both roll off around the same place together. Right? So they just add together constructively, right? You get a really nice stable bond between H2. Right? What if we do a 2s plus a 1s? So like, let's say lithium, right? Lithium would be 2s1. So what if we take lithium and we take hydrogen, right, which is in the 2s orbital, and this is in the 1s orbital. Right? So let's go ahead and do the same thing. Right? And again, lithium will be blue, hydrogen will be H. Right? This is in the 2s orbital, right? So the wave function changes signs. Right? So the wave function, oh, sorry, it needs to be in blue. The wave function changes sign here at long distance. And of course, the wave function for H doesn't at all. Completely symmetric. Yeah. Okay. So what happens when you add them? Well, you're going to take this positive amplitude, right? And you're going to add it to this negative amplitude, right? We get destructive interference. Right? So what we get then in the end when we add these two wave functions together, well, we get a little bit of addition here where these two are on the same side. So there's a little bit of hump here. So the net wave function gets a little bit of hump here, right? And then the place where this goes negative and this is positive, right? So most of this cancels out when we add these two. Add a positive to a negative contribution. So this thing is very close to zero in the middle, right? And eventually the hydrogen dominates and you get something that looks like this instead. This would be LiH. Right? So we have weak overlap in the center. But notice we have high probability near hydrogen. What can we say about this bond? Well, it's not perfectly covalent anymore, right? Because the electrons are being shared in the middle, right? The electrons have been polarized towards the H. Right? So what would we say about this bond? Well, we would say that there's a buildup of electrons around the hydrogen and a depletion of electrons around the lithium. Right? This is an ionic bond or a polarized bond. Right? And the reason why Li and H, one of the reasons why lithium hydride is such a reactive molecule, the lithium hydride is used as a base, the H- is hydride base. Right? It's because the covalent wave function for lithium hydride is polarized towards the H atom. Most of the electrons sit on the H, so that H has a very strong negative charge compared to it. Right? And that only comes from that in some sense, the major contributor to that polarization is nothing more than the fact that you're mixing a 2s and a 1s, and the 2s changes signs, so you get polarization near the edges of the bond and destructive interference in the center, right, which polarizes the electrons towards the edges. The wave functions don't overlap in this. Very simple. In some sense, we've already, that's not the only thing that's involved in electronegativity, but one of the reasons that we have electronegativity is due to this. It's due to a mismatch in orbitals, where it will polarize electrons to be on one end versus the other. That's just electronegativity. We'll look at it more carefully, of course, when we get to molecules, right? But we can just look at basic orbitals and we can already start to see kind of gen-chem bonding patterns just by doing some analysis. So these are just S's, right? So, but let's go back to that nodal-like structure again, right? So the idea is that in some sense, nodes are bad, right? The things that match best with 2s orbitals are other 2s orbitals, right? Because they oscillate in the same way, right? If this was lithium, both functions would be, one function would be positive. Oh no, actually they'd be opposite. That's why lithium isn't a strong bond, because lithium would be under where the other lithium is positive, and they'd be mirrored and they would just cancel each other out, right? So lithium dilithium is not a strong bond because you basically have a mirror wave function and the whole thing cancels out. So lithium doesn't work for that express reason. However, you go down one to sodium. Sodium is 3s. 3s is symmetric. It goes up and then down and then up again. And so you get some additional attraction. You get some overlap between the 3s orbitals of sodium. Is that the thing that's below lithium? Yeah, sodium. Sorry. Sodium Na2 is a stable gas phase molecule, stable covalent molecule. The 3s orbitals actually align very nicely because of their oscillations, and you get some attraction, you get some overlap between them. Na2 is a very common molecule to make in the gas phase. Not common, but you can make it. Very hard to make lithium ion. That reason. Right. So overlap, wave function overlap between atoms explained qualitatively explains pretty much all of bonding. In fact, when we talk about bonding, we're going to think about these kinds of addition arguments. This is how we construct bonds, in fact. Right. Let's just look at two more examples, right? I had mentioned that the 2p and the 3d, they have this S-like bonding characteristic. And I just want to show you that to you. So let's look at 2p. Right, here's a great example, right? Let's do oxygen and hydrogen. Okay, and let's set this to be in a 2p orbital. And of course, H is in 1s. And I'll do the same color coding as before. Well, we have some ambiguities about which p orbital to pick. Okay, so let's look at two examples. Right? So there's three p orbitals, but two of them fall in the same class. So either let's define the axis system. This is the z-axis, right? So if we choose 2px or 2py, these wave functions are these p orbitals actually perpendicular to the bond. Right. So if we have our O here, its p orbital has a positive lobe like this and a negative lobe like this that changes signs. That's a negative sign on this side and a positive sign on this side. Okay. And then we have our H orbital, which is just a sphere. And it's positive everywhere. Okay. This is our H. So when we add these together, so this is either our 2px or our 2py, it doesn't matter. When we add them together, we have to add above and below the bond. And so we're going to add this to the top hemisphere of the sphere. So that's good. So we have some positive overlap on the positive, but notice that we have negative overlap on the bottom. Right? So we have a plus contribution to our overlap here, and an equal and opposite contribution on the opposite side that cancels it out. So this is non-bonding. Okay, so 1s plus 2px, 2py is a non-bonding combination. Right? Because of symmetry. Right? If I add the function above the plane, it's a constructive addition. If I add them below the plane, it's a destructive addition. It's a negative addition that's equal and opposite. So sum of these two is plus minus, and it's 0. Well, it's non-bonding. Right? Doesn't bond at all. Right? This is why, of course, in H2O, as we'll see, it's a little more complicated than that because we have hybridization, which we haven't talked about yet. But there are these lone pairs on oxygen that don't bond, so don't interact. They're sitting in effectively the X and the Y orbitals. And the H's are coming in along the Z-axis, and those two lone pairs are sitting in the X and the Y orbitals, right? There's additional hybridization that we haven't considered, that sp3 hybridization. We haven't talked about that yet. That contributes to it as well. But the idea is that the lone pairs typically are stored in the orbitals perpendicular to the bonding axis. This is where the lone pairs would go. Right. And then let's look at the final orbital, 2pz. And here we have an O in the middle. And now the orbital is aligned along the bond. Cut it off here. We have a positive phase here. Function is positive on the right side and negative on the left side. And this adds directly to an H orbital, a 1s orbital for our H atom. That's positive everywhere. Okay. So we have a positive lobe coming into a positive sphere. They add constructively. We get a bond, a covalent bond, right? So the final function that we would get would look something like this. Right, so this is the H, and this is the O. And we get some positive overlap in between them. And so this is a covalent bond. Right? Nice stable bond. Of course, it's nice and stable. It's H2O, right? Or OH. Ever OH, you can think of hydroxyl or water. All very stable. Not perfectly stable, right? It's easy to pluck an H off. There's always some equilibrium. The whole reason why acids and bases exist. And again, the reason why that is because most of the distribution of I actually have drawn this a little incorrectly. Because the H is very tight, there's very little distribution here. You can say it kind of rolls off like this instead. So there's more possibility for it to be, right? The electrons are polarized towards H or towards O. Something like that. And again, that's the way that typically works, right? We know that H is a little acidic. Okay, there's one more example I want to show you. Just to kind of drive this point home. And you see this in metals. Right? A very similar type of bonding in metals that looks very hydrogen-like. So chromium would be an example, just some sort of heavy metal, a D-block metal. The D-block metals. D-block metals have a special orbital, one of their Z orbitals or their d orbitals, is called the dz squared orbital. So here's your atom. The dz squared orbital has p-like lobes like this that are the same phase. And then it has this like ring, planetary ring around it of density that's an opposite polarity. And so you could say this is minus and this is positive. Right? This is what's called the dz squared orbital. Right? This would be like the 3dz squared orbital. Okay? Which is kind of like the pz orbital. Looks just like the pz orbital, except it's got this extra donut around the center atom. Right? And so you could take this orbital, right, and bring in another metal atom like this. Right? And you have this positive interaction, right, which would give you a net orbital, a bonding orbital. That shares density between the two atoms. Do a little bit of this around the ring. And then small lobes on the outside. This would be the addition. Right? And we have covalent overlap here. You've seen molecules like this in homework 3, right? Molecules like MO2, chromium dimer, ytterbium, molybdenum, etc. Right? You see these metal dimers, and they're nice, strong covalent bonds. You saw that, right? You saw that some of those metal bonds, they're just as stiff or very similar in stiffness to HCl, which is a very typical covalent molecule. And so you get this nice, strong covalent interaction between them. There are other interactions in these block metals that strengthen it, but this is the primary S-like one. It looks like two S's. I mean, you get these nice, strong single bonds between two metals that have dz squared orbitals that are not fully, that are somewhat if they have unpaired electrons. Right, and you form these double bonds, the single bonds. So the idea is that every new angular minimum state that appears, the 1s, 2p, 3d, 4f, 5g, 6h. Of course, those are irrelevant. There's no molecule stable atoms with 5g's or 6f's or 6h's, but if there were, all have this motif of interaction that looks that they have a set of orbitals, at least one, or sometimes more, that have S-type bond. Because those orbitals don't have nodes. They have an S-like shape, a nodeless S-like shape. And so they can interact very, very effectively together with very little cancellation or destructive interference. You get very nice overlap between the atoms. Why you see these strong bonds in situations that might seem odd to you, why you would get strong bonds. But this is the reason why these metal dimers in particular are so stable, or you can make them in the gas phase stably with nice strong covalent bonds, because they have, in some sense, this ability to bond like s orbitals, spheres, nodeless spheres, right? And that's the best thing that you can do for a bond, is to have maximum overlap without oscillations. Okay, any questions about this? All right, good. So this puts us in a very nice situation to tackle energy levels in class. We're going to tackle it historically. We're going to go look at some old spectra. Think about the way that people looked at hydrogen before they understood any of this. We're going to look at this really interesting story. People figured out the hydrogen spectrum before they even understood, before Bohr was even around. Bohr was a child. Niels Bohr comes up with this spherical orbit model to describe the hydrogen spectrum. He gets it right up to a point. But the physicists, the astronomers, the people who studied hydrogen before him figured out the spectrum of hydrogen without knowing any physics about hydrogen, how it works. They use, in some sense, pure numerology. They make up a formula to fit the data, and it fits beautifully. And for decades, they don't understand why that formula works. It just does. Not until Bohr in quantum mechanics that we can actually derive the formula that fits that spectrum. First principles. And what we find is that all those old astronomer numerologists that are just fitting a formula to data. They're just making data up. They're not making data up, they're making formulas up to fit the data. It turns out that the formula they make up for hydrogen matches exactly with what quantum mechanics is. Precisely. They get it right, but for the wrong reasons. Right, so we'll look at that, and then we'll look at the places where their predictions and Bohr's predictions and all of these things start to break down. We'll have to try to reinterpret spectrum from a different perspective, a more modern one. And so we'll think about those things next class. All right, have a good one, guys. Finish before 1:45. What a pro.
I'm back to hard R8s. I realized I forgot my flute there. Yeah. No. I'm parked at the wreck.
Why don't you go to the road, park in front of our Gary on like by the parking lot by the steps, you can go up the steps and then just from there.
Parking there ever.
Fair enough.
Plus I'm